Okay, thank you so much for coming here and thank you so much for being patient. We are trying to seat everyone and hopefully everything is comfortable. My name is Rohit. I am affiliated with the computer science department here, so I'm technically a computer scientist. But as you'll find out, that today's lecture is not just about computer science. It's actually something that involves a combination of mathematics and economics. Okay, so just a few minutes ago, Shomik was asking you, well, how many of you want to do computer science or basic sciences or economics? I see a vast number of you who are interested in engineering subjects and maths, but fewer interested in economics and humanities. I hope that number also grows. But the point of today's lecture is that mathematics, of course it's very useful, but the way we often see mathematics is in the form of these dry definitions and theorems, right? Sometimes just these theorems fall from the sky, definitions just come out of nowhere. You're like, okay, why is this happening, right? What is calculus and what is geometry? Where is all of this useful? Hopefully today, we'll see some of the real world applications of mathematics, okay? And specifically, we'll talk about application of mathematics in fairness. How do you divide something fairly among a bunch of people when these people have some preferences over the things to be divided? Okay. So before we get into the lecture, I just want to get a sense of what do we think, when I say the word fairness, what are some of the things in your daily life that you would divide fairly? Right? You might come into these situations where you divide stuff fairly among a bunch of people, right? What are some of those situations? Let's hear from you. Just raise your hand whenever you think, some situation of fair allocation arises in your life. Yes? Tell me your name, your school, and your answer. Okay. You can speak on the microphone, yeah?
My name is Sasha.
Yeah.
I'm from Delhi, and I think that we would divide the pieces of pizzas fairly.
Pieces of pizza. So you're going out with your friends, you order a giant, 12-inch pizza, and everyone just picks out some slices. So, okay, that's a very relevant example of fair allocation of some resource. Any other examples? Yes? Over here.
Good morning, I'm Adyan Chanchal from IIT Delhi, and I would say the fair distribution is about bills.
Bills?
Yeah.
Okay, so among whom? Bills of what kind and among
when
whom?
we are in cafe or something, we are distributing the bills.
Okay, so your friend there has had pizza, now you have to pay the bill, huh? Okay, alright, fantastic. Okay, great example, right? So you go out with your friends, you order all the delicious food, then you realize, oh, maybe we over-ordered. Things cost money, now how do we split the money among us? That's a fair allocation question. Excellent. Any other examples of situations where you have to divide stuff fairly? Workload. What kind of workload?
As a teacher, we are from the different departments. We are getting some work from headquarters.
Right. So as a teacher, I can totally relate to what you're talking about, right? So as teachers, we have to teach courses. Some courses are huge, right? In IIT, we teach courses with even 1,200 students, right? And then some are smaller courses, more specialized courses, right? So, in the department over here and in schools in many places across the country, the teachers have to figure out who is teaching which class, right? Because different classes require different kind of workloads. How do you distribute this workload fairly among the teachers? And the teachers can have very different preferences over these resources, right? Some people might actually like to teach bigger classes, right? Some people maybe not so much, right? They might want to teach a smaller group on a specialized topic and so on. So different people have different preferences. How do you allocate these resources among the people such that the final division is considered fair by everyone, right? So great example. Any other examples? Let's hear maybe one or two more. At the very back, yes. Just shout out your name, school, and your answer. Okay, yeah? Divide respect equally, okay?
Irrespective of caste and economical status.
Fantastic.
Equal
Respect everyone, right? Okay, great message. Any other example? Yes, at the back. Your name?
Hello. Hello.
Okay.
Hello. Hello. Okay. Hello.
Budget division by the government among, let's say, various ministries, various projects, etc. Right? So, great example, right? So again, a fair allocation of money. One example we heard was that of the restaurant bill, right? The other example is if you are the government, you have to figure out which department or which ministry gets how much money. You have to do so fairly because everyone wants all the money, but that's not possible, right? You have to be fair across various departments. Yes? Yeah. Excellent example. So like, let's say natural resources, water, fossil fuels, minerals, forests.
And there are so many factors like when you are distributing minimum requirement.
Absolutely,
So
absolutely.
everybody should get.
Exactly.
You have plenty, but there are the people who don't get.
Yeah. How do you divide natural resources fairly among various interested parties? That's a great example. Okay, maybe one final example. Yes, please.
I'm Shaurya from KVBSF Camp Chawla, and as a student, I think the number of hours for study, we divide it as the subject which are strong for us and which are weak.
Right.
We divide the hours fairly.
Right. So the resource here is time, right? So we have heard of natural resources and money as being the resources. Here the resource is time, and you have to divide or split your time fairly across various subjects depending on the needs. Okay, some subjects require more attention, some not so much, and so you have to be careful about that. Okay. So great examples. I'm sure there are many more examples that we didn't have the time to get to, but hopefully everyone is convinced that fair division of resources is an important problem, right? It's a practical problem. It arises in our daily lives, and you need a concrete way of solving this problem. Why? Because it's a very subjective notion, right? Something that is fair for one person may not be fair for another person. So how do you agree on a fair solution, right? So to solve this problem, we are going to use maths. We are going to write formal definitions of what it means to be fair, and then we'll use some clever mathematical ideas to come up with solutions that satisfy those definitions. Okay, because math is uncontroversial, right? So if you prove something in math, it stays there, no one can object to it. Okay? So math is going to empower us to come up with fair solutions. Okay? And the two situations that I want to talk about, of fair allocation in today's lecture have to do with food, obviously, right? Not so much pizzas, but this problem is more generally called cake cutting and division of money among a bunch of flatmates. This is called the rent division problem. Okay? And we are going to use maths, and specifically you will see triangles are going to play a big role in coming up with a fair way to divide rent so as to achieve harmony among the flatmates. Okay? So this is the broad outline of what we are going to talk about today. Okay? And anytime, if anyone has any questions, just raise your hand, shout out, and I'll try to pause whenever. Okay? Excellent. Okay. So, two problems we are going to talk about, cake cutting and rent division, okay? So let me start with the first problem, which is cake cutting. It has a playful name, right? We all must have cut cakes in our lives, but turns out it's a formal math problem, right? Mathematicians study this problem. This is literally the name. I didn't make anything up, okay? So it's all fun and games, but this is a serious mathematical problem. Let me try to describe it in an informal way nevertheless. So imagine that you have a birthday party, okay? And there's a cake, there's a bunch of kids in attendance. And now you have to divide this cake among the kids in a way that is fair. Of course, every kid wants the entire cake, right? But you can't give the entire cake to everyone because you don't have that much cake. So you have to divide the cake. Now, what is a good way to divide the cake among the kids, right? So that no kid complains. So, in particular, one notion of fairness could be the following. You want to divide the cake among these 4 kids, let's say, such that once you have done the division and once you have assigned the pieces, the yellow kid thinks that whatever piece it got, it likes that piece more than whatever piece any other kid got, right? So the yellow kid thinks, okay, my piece is the best according to my preferences, okay? If that's the case, then the yellow kid would be very happy, it won't complain. Yes? Yeah? Okay. Likewise, at the same time, we want that the blue kid also feels the same about its piece, right? The blue kid looks at its piece, it thinks, oh, my piece of cake is better than whatever every other kid got, right? So I won't complain. Okay, and according to my preference, blue kid's preferences could be very different, right? Maybe the yellow kid likes chocolates and strawberries, and maybe the blue kid likes the frosting and some sprinkled toppings and whatever. Okay, so different people can like different things. Okay, and likewise, we want the same to be true for every single kid. Every kid should feel that whatever piece it got is at least as good as that of any other kid, right? According to their own preference. Okay, is the idea broadly clear to everyone? Right, everyone is happy with what they got. So the key word here is envy, right? We want a division in which no kid envies another kid, right? No one wants the piece that someone else got. They are quite happy with what they got as per their own preference. Okay? So here's the problem. Given this cake, it could be a very complicated object. We want to divide it among the kids such that the division is envy-free. Okay? There is no envy among the kids. All right. So let's try to start thinking about this problem. Okay? Let's say we are in this very simple world where there are just two kids. Okay? And there is just this cake which I've drawn as this very dull gray rectangle. But you can imagine, you know, it's basically, my drawing skills are not that great. Okay? So imagine there is a very nice looking cake in between, but I've just drawn it as this boring rectangle. Okay? Now we have to divide this cake among the two kids in a way that is free of envy. How do we do that? Anyone? Raise your hand. Any thoughts? Yes. Yeah, go ahead. Sure, go ahead.
My name is Kushika. I'm from KV Sector 8 SPG.
Okay.
My preference is we have to cut it into two equal pieces from the middle.
Okay. From the middle. You mean the geometric halfway point? Is that what you mean? And then do what? Once you cut it into two parts, what do you do?
My name is Krishna Soni. I'm
Yeah.
from KV Andrews Ganj. And I would say that one kid should cut the cake into two pieces such that he thinks that both the pieces are equal.
Excellent.
And then the second kid can choose whichever piece he wants.
Fantastic.
The first kid would not have any envy with the...
Okay, and why would that be a good solution? Why are both kids happy with what they got?
Yeah, so first kid is happy with whatever piece, and the second...
Because they equi-divided.
Yes.
Okay.
And the second kid can choose whichever piece...
Whichever they like better, so they wouldn't envy. Fantastic. Great answer. So this idea that is being suggested is called the I cut, you choose method. Okay. I'm sure many of you would have, at least those who have like siblings of a somewhat similar age must have played this game, right? Anytime you have to divide a resource, so one of you splits it into two equal halves according to their preference, and the other one picks whichever they like better. Okay, so that's the game we are playing here. Okay, so let's say we invite the orange kid to split the cake into two parts. This need not be at the geometric half, right? Maybe the kid likes the stuff here a lot, and the stuff here maybe not so much. So we are splitting it at the point where the preference is halved, right? Two pieces that are equal in the preference of the orange kid. That split may not happen at the geometric half, okay? Because preferences can be very complicated, okay? Anyway, so orange kid makes this equi-division, and then we invite the blue kid to pick whichever piece it likes better. Let's say it likes the right piece better. So it's going to get the right piece, okay? And we are going to give the other piece to the orange kid, right? And this is an envy-free division. Why? Because the blue kid picks the piece that it likes better, so it won't envy the orange kid. And the orange kid equidivided. It doesn't care which piece it gets. Yeah, they're both of equal value. Okay. So when there are two kids involved, we can solve the envy-free cake cutting problem very easily, right? Just by making one cut. But now imagine what happens when you have 3 or more kids involved. Okay, it's a bigger birthday party now. Okay? How would you come up with an envy-free division? You might think that, okay, let me invite one of the kids, let them cut the cake into 3 equal parts according to their value, and give the other 2 bits to the other 2 agents or other 2 kids. But that may not work, right? Because there might be envy between the other 2 people. Okay? So it turns out this is not such an obvious problem to solve. It does require a bit of thought. And one of the goals of this lecture is going to be to show you how you can solve this problem, not just for 3 kids, but for any number of kids. Okay, no matter how big your birthday party is, you can always divide your cake in an envy-free manner. Okay, and that's where maths and triangles will come in. Okay, so this is question number 1 that we want to solve today. Right, so that's the cake cutting problem. Here's second question that we want to solve today, which is called the rent division problem. So let me describe that. Imagine you have 3 people who are looking for a flat. Okay, these are 3 friends who are looking for a flat to rent. Okay, a 3-room flat. And let's say they like this one. So this is a 3-room flat. Okay, room 1, room 2, and room 3. And these rooms are not all the same. Okay, they are somewhat different in their features. The first room, as you can see, is the biggest room. You know, it has a lot of space, but it does not have any windows. It just has one door. Okay, so the ventilation isn't that good. The second room is well ventilated, but it's not that big. Okay, and the third room has the most important human necessity, which is Wi-Fi. Okay, now these 3 friends may have very different preferences, right? Someone might want to live in a ventilated room, someone might want high internet speed, someone might have a lot of stuff, so they need more space, and so on. Okay? So different people might like different things. Our goal is the following. Okay, so first of all, imagine that the rent of this apartment is 1,000 rupees. I know we are in South Delhi, this is not possible, but you know, just imagine it, okay? Okay, so say 1,000 rupee rent, these 3 people have to pool in the money. Okay, so now between them, they have to figure out who gets which room and how much do they pay for that room. Okay, so 2 things, the allocation of the rooms and the pricing of the rooms. Okay, so for a possible solution could be, let's say, person B gets room 1, person A gets room 2, person C gets room 3. And let's say they decide that person B, who is getting room 1, pays 500 rupees, A pays 300, C pays 200. Okay, this is one possible solution. When is this solution a good solution? Well, we would call it a fair or a good solution if the following happens. So we are looking at B's preferences, we are looking at B's thought process, right? B is thinking that I like my room at the current price, right? So I like room 1 at 500 bucks over getting room 2 at 300 bucks and room 3 at 200 bucks, right? I prefer my room price pair over the room price pair of anyone else. If that's the case, then I'm happy with my life. I do not envy anyone. Yes? Make sense? Yeah? Similarly, we want A to think that its own room price pair, room 2 at 300, is a better deal for A compared to B's room at B's price or C's room at C's price. Okay? In that case, A wouldn't envy B or C. Okay? And C should think the same about its own room price pair. Okay? So this is the kind of solution that we are looking. We want to assign people to rooms and put price tags on the rooms such that everyone believes my room price pair is better than anyone else's room price pair. Okay? If that's the case, then no one would envy anyone else. This would be what one would call an envy-free rent division. Okay? Make sense? Yeah? So sounds very similar to the cake example that we saw before, except that instead of cake, here we are dividing money. Okay? And in cake, you want more and more of cake. It's a desirable resource. For rent, you want to pay as little as possible. It's an undesirable resource. Okay? So that's the qualitative difference between cake and rent. Okay? But there is some similarity in how these problems are framed. Everyone with me so far? Problems make sense? Yes? Fantastic. Okay. So these are the two problems that we are going to be thinking about today. And as I said, math is going to help us, and specifically triangles are going to show up in solving both of these problems. Okay? So now let me get to the mathy bit, and then I'll come back to how you can solve each of these two problems. Okay? Okay. So what is the math result that we are going to use? So this result is called Sperner's lemma. Sperner is the name of a mathematician. It's a fairly old result. Everyone knows what a lemma is. Has everyone heard the term lemma? Have people heard the term theorem? Theorem everyone knows? Yeah, what is a theorem? Anyone? Just shout out. What is a theorem? Yeah, it's a mathematical statement that you can provide a proof for, right? Okay. What is a lemma? Has anyone heard of lemma? You have, okay. What is a lemma? Excellent. So both theorems and lemmas, they are mathematical statements which you can provide a proof for. Okay, these are provable statements. You call a statement theorem if it is an important or a major insight or major observation. If you are using a result to prove something else, as a helper result, this smaller result is called a lemma. Okay, it's sort of a side cast. Okay, the main hero is theorem, the sidekick is a lemma. A lemma is useful in proving a theorem. Okay, but otherwise these are the same things. These are both results that you can prove. Okay, yeah. Okay, so this result that I'm going to call it is famously called Sperner's lemma because this lemma is used to prove many other big theorems. Okay, it's a helper result, but it's sufficiently important in its own right. So maybe you can actually call it a theorem, but this is how things are named. Anyway, so this result is about triangles. Okay, so imagine a giant triangle like this, and imagine splitting this giant triangle into smaller triangles. Okay, so something like this. Okay, so this outer triangle is what I'm going to call the giant triangle, and these little ones here, 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 these smaller triangles I'm going to call elementary triangles. You can also call them baby triangles. Okay, these tiny triangles. All good? Okay. Now we are going to assign some colors or numbers to these points here. This one, this one, this one, this one. Right? These are things that I'm going to call the vertices. These are points of interest in this picture. So I'm going to label these points in a way. How? First, I'm going to assign labels to these outer vertices. These are what I'm going to call the main vertices. Okay? And I'm going to make sure that they all get distinct labels. Okay? So 1, 2, and 3. All right? No repetitions. Cool. Now I want to assign labels to these points on the boundary here. And the way I can assign labels is that for any point on the boundary here, let's say this boundary here, Can people see the pointer? The red dot moving around? Okay, yeah. So for any point on this boundary, I can only assign to it one of two labels, either this extreme point or that extreme point. Okay? So any point here gets label 1 or 2. Some can get 1, others can get 2, that's fine, but it cannot get 3. Okay? Similarly, any point on this boundary must only get the label of one of its extreme points, either 2 or 3, but definitely not 1. Okay? And so on. Okay? So any such labeling is a valid labeling for us. This is called a Sperner labeling because it's Sperner's lemma. Okay? Are the rules clear? Right? Any kind of numbers you can come up with that obey these rules, that's a good set of numbers. Excellent. Okay, so this is one example of labeling this. Check that I haven't violated any rules here. Yeah, this is consistent? No cheating? Yeah, okay, good. For the points in between, right, in this inside area, you can assign them any labels, no rules whatsoever. Give them any numbers you like, doesn't matter. Okay? So this is an example of the triangle that we're going to be working with. Okay? Now for any such triangle which is labeled according to these rules, Sperner says that there must be a baby triangle which sees all three labels, 1, 2, and 3. Okay? Can someone spot such a baby triangle for me in this picture? Yes. Just shout out. The person at the back, yeah? Go ahead. Third row. This one? Fantastic. Okay? Thank you. So here is a fully labeled triangle, a fully colored triangle. Okay? So this lemma says that anytime you have a giant triangle which is split into these smaller triangles and you label it according to these rules, you will always find a tiny triangle which has all three labels. Okay, a colorful tiny triangle. Is the theorem, is the statement clear of the lemma? Any questions about the lemma? All good? Okay, good. So this is the key result that we are going to use to come up with fair solutions to cake cutting and fair solutions to rent division. Okay? So let's do that. Okay? So triangles. All right. Cool. So let me start with the second problem first. Let me try to tell you how you can come up with a fair way to divide a rent using Sperner's lemma. Okay? All right. So recall the problem. The problem was that you have 3 people looking for a flat, right? They have to divide the rooms amongst themselves and come up with a pricing scheme that is fair according to everyone. Okay? Cool. So, for example, this allocation of people to rooms and determining who pays how much, such that the final solution is envy-free in the eyes of everyone involved. All right? Okay. Cool. So let's see how we can use Sperner's lemma to solve this problem. So I'm now going to draw 2 triangles, 2 of those giant triangles that you just saw. Okay? One of them is called the ownership triangle, and the other one is called the preference triangle. Okay? We are going to play with 2 triangles now. Okay? So the ownership triangle looks like this, right? It's again the same giant triangle which is subdivided into these baby triangles. Okay? Now, to the vertices of this big triangle, I'm going to assign labels which are the names of the people involved. Right? These are the 3 flatmates, A, B, and C. I'm going to assign to each vertex the name of exactly one of the flatmates. However, I'm going to be a bit clever about it. Okay? Does anyone see an interesting pattern in this assignment? Exactly. So the way I have assigned these names is not arbitrary. I have been careful to do that. You know, for any little triangle, it sees all 3 names, A, B, and C. All 3 flatmates appear. You look at this one, you look at that one, you look at that one, and so on. Okay? So this is a special, cleverly constructed triangle. Okay? So this is one of the triangles that we are going to play with. Okay? Is the construction clear? Yes? Yes. Excellent question. I was hoping someone would ask me that. What's your name? Karthikeyan. So Karthikeyan is asking, look, you have just assigned labels to this triangle, but this does not seem to obey the Sperner rules, right? Sperner said that the outer vertices should be distinct, so that's fine. But on the boundary, if you're assigning A here and B here, you should only give A and B here. Why do I see a C here, right? So the answer to that is that I'm actually not going to apply Sperner on this. I'm going to apply Sperner on the other triangle. This is just a helpful tool to help me apply Sperner on the other one, okay? So excellent observation. This is not where we'll apply Sperner, so this can have any labeling. Is the point clear? Okay? Fantastic. Okay, so let's come to the preference triangle, okay? So I'm going to draw another such big triangle there in just a second, but to motivate, to tell you how that triangle is coming in, let's imagine the three-dimensional coordinate system. Everyone has done geometry here, right? Everyone knows three-dimensional geometry, x, y, and z axis. Yeah? Okay. So that's exactly that, x, y, and z axis, okay? On this axis, you'll find points like 1, 0, 0, right? So x coordinate is 1, y is 0, z is 0. Similarly, on the y-axis, you have 0, 1, 0. On the z-axis, you have 0, 0, 1. Yeah? Everyone familiar with this system, right? Coordinates? Okay, cool. So for us, okay, so let's try to first join all of these 3 points by means of a slicing triangle. Okay, so if I join these 3 points, you can imagine that there's a nice triangle that connects all 3 of them, right? It is a slice that cuts through your 3-dimensional space. Everyone can imagine that? Yeah, and it's going to be a triangle, right? 3 points and so on. Cool. Now for us, these are not just any x, y, and z axis. These axes have some meaning for us. Okay? What is that meaning? So the meaning is that the x-axis, I've always colored it red, meaning it corresponds to room 1. Okay? The second number is blue, meaning it corresponds to room 2. The third coordinate corresponds to room 3. So every axis corresponds to some room. Okay? Okay. And what do these numbers mean? So these numbers indicate how I'm pricing the 3 rooms. Okay, remember I had a rent of 1,000 rupees to pay. I have to decide how much of that 1,000 is paid by owner of room 1, how much of the 1,000 is paid by owner of room 2 and owner of room 3. Yes? So I'm dividing 1,000 across 3 rooms. Yeah? So in other words, I'm trying to come up with what fraction of rent is paid through room 1, through room 2 and room 3. Yes? Okay? So these numbers here denote precisely that fraction, right? What fraction of rent is paid through each of the 3 rooms. Okay? So the way you should read these numbers is the following. So let's focus on this number here, 0, 1, 0. Right? So room 1's number is 0, room 2 is 1, room 3 is 0, meaning the entire fraction of the rent is assigned to room 2. Okay? So this suggests a pricing scheme where room 2's price is 1,000 rupees and rooms 1 and 3 are absolutely free. Okay? That's what that point means. Everyone happy? Yeah? Okay. Similarly, this point here means that the entire rent is paid through room 1. Rooms 2 and 3 are absolutely free. Alright? And likewise this point here. Okay? Now, what do the points in between denote? Can someone tell me? Just raise your hand. Yes. Sorry? Equal split. So what is an equal split? 1/3, 1/3, 1/3. So that would be one of the points on this triangle. Are there any other points in this triangle? Exactly, right? So basically every point on this triangle is of this form, x, y, z, right? Some variables which all add up to 1, right? And x denotes what fraction of the rent is paid through room 1, Y denotes what fraction is paid through room 2, and Z denotes the fraction through room 3. Right? So these fractions all add up to 1, right? You have to pay the entire rent. You're figuring out how to divide this one fraction into 3 parts, X, Y, and Z. So all points on this triangle capture all possible pricing schemes. Right? All of those fractions are sitting here on this triangle in between, like boundaries as well as the inner points. Everyone sees that? Yeah? Okay? Okay, good. So now I'm just zooming into that triangle. I'm leaving the 3-dimensional world behind. I'm just focusing on the 2-dimensional picture. Okay, just that triangle, that slice that we were looking at. Okay? So remember, again, the extreme points of this triangle are 1, 0, 0, 0, 0, 1, 0, 1, 0. And now these points have some meaning, right? The fraction of the rent paid by each room. Okay? So as someone was mentioning, you can also imagine an equal split. So that point is right smack in the middle over here. Right? 1/3, 1/3, 1/3. That point is present on this triangle. Okay? You can imagine a more unfair pricing scheme. Let's say, I don't know, 57% of the rent goes to room 1, 37% to room 3, and basically room 2 is free, almost free. Right? So that pricing scheme is also there. Any possible pricing scheme that you can come up with, it's there on this triangle. Yes? Everyone believes me? Yeah? Okay. Let's hear a louder yes. Everyone believes me? Yes. Fantastic. Okay, great. Everyone with me. Good. So all pricing schemes are here. I have to find that pricing scheme which is fair. Yes? Okay. So let's do that. So now this pricing based triangle, right? I'm going to split it, I'm going to subdivide it in exactly the same way as I did for the ownership triangle. Okay? I'm basically going to create a mirror image of the ownership triangle on the right. I can do that, right? Okay? So the division is exactly identical, although the labelings would be different now. Right? Remember, I told you we are going to apply Sperner here, so the labelings have to differ. Okay? Let's see how you label this. So, I'm going to use the left triangle to help me label the right triangle. Okay? How? I'm going to look at, so let me just move forward. I'm going to look at any point in these triangles. Let's say the topmost point. Okay? The owner of that point in the left triangle is person A. Yes? And the pricing scheme of that point is 1, 0, 0, meaning room 1 is being offered at 1,000 rupees and rooms 2 and 3 are free. Right? Okay. So now, for any point and its mirror image point, I'm going to ask the owner on the left, well, you see this pricing scheme, tell me which room is your favorite. Okay? If room 1 is available at 1,000 rupees and rooms 2 and 3 are free, point to the room that you like the best. Okay? Make sense? Right? Because your preferences depend not only on the rooms, but also on prices, right? You might like a room, but if it's too costly, you might like something else. Right? So I'm offering rooms and prices both, right? I'm offering a menu of options, and you tell me, okay, I like room 1 at this price, room 2 at this price, or room 3 at that price. Okay? So this is the question that I'm going to ask this person for the point on the right. Okay? All right. Okay, so let me just go back. So for each vertex in the ownership triangle, right, so this vertex, this is a vertex, and so on, I'm going to ask the owner is the label of that vertex on the left. Tell me your favorite room at the pricing given on the right side triangle at the same point. Okay? So hopefully let's do one example and hopefully it will become clearer. So like I said, at this pricing scheme, I ask person A, tell me your favorite room. Now suppose you were person A. You see room 1 at 1,000 rupees. You see rooms 2 and 3 for free. Which one would you pick? 2 or 3, right? Everyone's cheap here, right? Everyone just wants rooms for free. I mean, no quality control whatsoever. Very disappointing. Okay, yes, but that's what everyone would do. right? If you see something for free, you point to it, right? Very natural. So that's something that we are going to assume also, that our kids, right, our flatmates or our agents, they also have this kind of behavior. They are miserly, okay? They see a free room, they point to it. No matter how good the pricey room is, and no matter how bad the free room is, you see a free room, you point to it. Okay? All right, okay. So now if I ask person A this question, person A would say, I'm happy with 2 or 3, but I definitely don't like 1 because it's pricey. 2 and 3 are free, either of them is good for me. Yeah? Fantastic. Let's move to a different point. So now for this point here, the owner is B. Look at its mirror image. That's 0, 1, 0. So to person B, we are asking, well, room 1 is free, room 3 is free, room 2 is $1,000 bucks. Tell me which room you like the best. What's the answer? 1 or 3, right? So either of them are good, but definitely not 2. Yeah? It's miserly, right? Our flatmates are cheap, so, okay. Likewise, what would C say? 1 or 2. Excellent. Now comes the more interesting part. What about the points here? Right? So suppose I'm looking at this point. I'll ask person B, whatever the pricing scheme at that point is, tell me which room you like the best. Yeah? So what would person B say? 1 or 3. Why? So is there a room that is free? 3 is free. Why? Who said 3? You should explain to me why. Sorry, yes, please. Yeah, so 3 is here and here, but why should, at this point, why should 3 still be of, room 3 still be free? What is the reason? Yes. Are you raising your hand? Okay, maybe not. Who wants to help me? Yes, please. Let's hear from, at the back. Go ahead.
So at the time of plotting the triangle, we just saw that we were plotting the third one's price in x-axis.
Exactly.
And this line, this edge lies in the yz plane.
Remind me your name, please.
Karthikeyan.
Karthikeyan. So Karthikeyan is spot on, right? So Karthikeyan is saying, remember how we constructed this triangle, right? This is not just an arbitrary triangle. It came out of the axes, right? The 3-dimensional axes. Yes? So if I go back, okay, my pointer doesn't work. All right. Let me go back and remind you of the, so any point here was connecting this extreme point and that extreme point, right? So any point here must have its z coordinate to be 0, right? Because you may have studied the equation of a line. If it connects 2 points, then any point of the line is, say, some x times left point plus some y times the right point. Right? It's a line, it's a linear object. So that's what any point on the line looks like, yes? From geometry? Yeah? So that's what we are using, right? Any point on this boundary which is connecting these 2 extreme points, its third coordinate must be 0, right? The first 2 coordinates might change around, but the third one is 0, yeah? Which means for any point there, which room is free? Room 3, right? The one corresponding to the third coordinate. So for all these points here, room 3 would be available for free, but rooms 1 and 2 may have some prices, some strictly positive prices. Yeah? So if you ask anyone on the boundary which room you like, no matter who the owner is, they'll always say, give me room 3. Yeah? All right, that's what we're going to do. So for any point on this boundary, because it's a combination of these points, so it looks like some x comma y comma 0, right? Some fractions here, but this is definitely 0. Yes? Yeah? So for anyone here, they would prefer to go with room 3, so that's what we go with, okay? Okay, now tell me what happens on this boundary here. What do people like on the bottom edge? 1, right? For the similar reason. So the first coordinate is always 0, right? Similarly on this edge, people like 2, and this is a one only edge. Is the construction clear? Right? So this is how we are labeling this triangle. Okay? Okay. Now I told you we are going to apply Sperner to this one. Does this look very Sperner-like? Can I apply Sperner here? Who thinks yes? Okay, a few hands. Who thinks no? There are only two possible answers. Okay, so whoever thinks no should tell me why. Who is in the no camp? Yes, go ahead.
Here we have choice.
Exactly. Here we have, like, we said, okay, the three outer vertices must have distinct labels, and everything on the boundary should be one of the two, right?
And the vertices can be same.
Exactly. So here, it's somewhat problematic, right? In Sperner, I fixed the labeling of this, this and that, and over here it was an OR. This or that, right? So the OR condition was on the boundary, and the main vertices were fixed. This is the opposite. The OR is on the vertices, and the boundary is fixed. Right? So it doesn't look like Sperner. Right? It's not like we can just directly apply Sperner to it. Okay? So this is the first complaint you might have. Like, hey, did you just waste our time? Right? We listened to you for Sperner, and then you show us this, and it has no Sperner in it, so why did you take us through the trouble? Yes? We will do that in a second. Excellent. What's your name? Say it again. Srijan. Okay, so Srijan is looking sort of much ahead in my slides, and he has an excellent idea which we'll come back to in a few minutes. Great. Okay. But for now, I hope everyone is convinced that this doesn't look very Sperner-like, so seems like a lost cause. The second complaint you might have is, okay, somehow, let's say, we somehow apply Sperner, we somehow come up with this fully colored baby triangle. What use is that? Right? Even if you give me a fully colored triangle, what do I do with it? I wanted an NV-free rent division. What do I do with a triangle? What use is it of me, right? Why do I care? Okay? So let me answer this second question first. Let me try to convince you that it makes a lot of sense to come up with a fully labeled baby triangle in this picture. If you were able to find it, right? That would be great, because that would solve your problem. And then we'll see how to find it. Okay? So let's first understand why do we care, and then we'll see how to find it. So why do we care? Okay. So suppose someone gave to you a fully labeled triangle. Okay? Let's say something like this. Why is it interesting? Why do you care? Well, remember what each vertex means. Each vertex corresponds to a pricing scheme, a set of price tags for the three rooms. Yes? So this vertex is a pricing scheme, this one is a different pricing scheme, this one is a different pricing scheme. Okay? If I give to you a fully labeled baby triangle, what I'm telling you is a bunch of three pricing schemes, right? Three different ways to price your rooms, such that under one scheme, the owner of the other triangle prefers room 3. Under this scheme, the owner prefers room 2. Under this scheme, the owner prefers room 1. Right? But here's the key observation. If you go back to the ownership labeling, remember all the labels were different. Right? A, B, and C. Okay? So this kind of a colored triangle would say that at this scheme, agent A prefers room 3. At this scheme, B prefers room 2, and the other scheme, C prefers room 1. What you would want is a single pricing scheme where that happens, right? If I give you a single point in this triangle where A prefers one room, B prefers another, C prefers another, that would be NV-free pricing scheme, right? Because we ask everyone, point to your favorite room. If everyone points to different rooms, that means no one envies anyone else. Yes? So what I'm looking for is a single point where different people point to different rooms. But what I'm giving you is 3 points where different people point to different rooms. So that's not quite what we wanted, right? There's a gap between what we wanted and what we're getting. Okay, right? So just to reiterate, suppose we come up with the solution, then what that would mean is at this pricing scheme, so at these prices, let's say, agent A prefers room 3, at slightly different prices, B prefers room 2, and at slightly different prices, C prefers room 1. That's what it would mean. But we wanted a single pricing scheme, not 3 pricing schemes, right? What do? Just shout out your suggestion. Maybe someone who hasn't spoken before, in the interest of fairness. Someone who hasn't spoken before, you want to pitch in with a suggestion? Anyone? Raise your hand. Centroid. So what is a centroid? Connection of 3 medians. So why is it of interest to us? Yes, so then the prices are equal, but maybe at those prices, 2 different people prefer the same room, right? Because preferences can be complicated. So our goal is not just to split the money equally, it is to split the rooms plus money equally so that everyone is happy with what they got, right? So it's not clear if same prices would give us an NB-free division, but that's a good first thought. Anyone else? Exactly, we could basically repeat the same exercise, but this time with much tinier triangles, right? Much more finer triangulation, right? So here there's a lot of gap in the prices, but what if I repeat the exercise with much tinier triangles, right? Sperner didn't assume anything about the sizes. It just said anytime you have a triangle labeled in a good way, there exists a baby triangle, right? Let me start with a different triangulation, which has much tinier baby triangles. I repeat the exercise, I get this triangle, right? And now I can keep going, I can keep making things finer and finer and finer until I end up with pricing schemes of this form, right? And these are basically the same, right? Up to a variation of a rupee. Yeah? Yeah? So what we are getting is not an exactly NB-free division, but an approximately NB-free division up to a rupee here and there. Okay? But then why is it useful? Well, what is a rupee among friends, right? A rupee you can tolerate. Okay? So up to a rupee, you can come up with an NB-free solution, right? Okay? And if you make this even more finer, you'll get an exact solution, but let's not get into that. Okay? Is the construction clear to everyone? Okay? So if I produce to you a fully labeled triangle, then you're good, right? Now the whole game is how do we guarantee a fully labeled triangle? Yes, that's what I need to tell you. Okay, so let me tell you why. Okay, so we have answered the second question, why care? Now the first question, well, how do you apply Sperner? Okay, so the hint there is to think outside the box, okay? And here's how to do it. So remember, this was our labeling, this was the preference triangle, yes? Let's shrink it a little bit. Why? Because I'm going to embed this in a bigger object. I'm going to create a bigger triangle outside my preference triangle in an inverted manner. Okay? Why not? We can do that. How do I label the vertices of this bigger triangle? Well, let me just do whatever Sperner wants me to do. I'll give distinct labels to the 3 vertices. However, I'm careful. So I give 1 to that vertex which is closest to the 1 only side, 2 to the 2 only side, and 3 to the 3 only side. Okay? That's how I give the labels to the vertices. Now I drop edges from each main vertex to the vertices on its closest boundary, like this. Okay? So I drop edges in this manner, then I drop edges from here, then I drop edges from there. Okay? So now what I have is an even bigger triangle which is also triangulated, right? Which is also subdivided into these triangles. Yes? Okay. But it's not clear what use is all of this, right? My goal was to find a fully labeled triangle here. Now I have made your life harder by creating even more triangles, right? It was already not clear, and then I've puzzled you even more. So where are we going with all this, right? Okay. So here's what we are going to do. We can apply Sperner on this bigger outer triangle. Why can we do that? Sorry? Say it again? Because I'm obeying the rules, right? I'm giving distinct labels to the outer vertices, and there are no boundary vertices. So it vacuously satisfies the Sperner conditions, right? There is nothing to check, so it satisfies Sperner, right? There is nothing on the boundary here, okay? And inside, remember, you can have any coloring, Sperner doesn't mind, okay? So we can apply Sperner on this bigger triangle. What does Sperner tell us? That there must exist a tiny triangle somewhere which has all three colors, right? We wanted to find a tiny triangle somewhere here, but now we have more triangles to deal with, right? We have these and those and those. We want to argue that none of those outer triangles can be fully colored, right? Why is that true? Is it possible that one of these or these or these triangles happen to be fully colored? Is that possible? No. Who says no? You say no. Okay, why? Yes.
And let's say that the one of the vertex 3
Yes.
have 1 and 2 on the other vertexes. But
Right.
if it has 1 and 2 on the other vertexes, then it will not be a 3 only vertex.
Exactly. That's not possible, right? So turns out that none of these outer triangles can be fully colored. Why? Because look at this, right? One of these long, slender triangles can certainly not be fully colored because each of them has two vertices which are both 3, right? This is a 3 and everything here is a 3. So any such triangle cannot be a fully colored triangle, right? These are ruled out. Yes? Similarly, these slender triangles and these slender triangles, they're also ruled out. Okay? So all that you are left with now are these flatter ones. Yeah? But even they cannot be fully colored. Why? Let's consider this one. This has a 3 and a 2. You need a 1 on the third vertex, but you have 2 or 3 on the third vertex, definitely not 1. Right? So again, this triangle cannot be fully colored. So if there has to exist a fully colored triangle, it better exist somewhere in this white region. It definitely cannot exist in the gray region. Everyone happy? Yeah? Okay. So then apply Sperner, right? Sperner says such a thing must exist, and we pick that. And remember, that is all we cared about, right? Once we identify a triangle like this, we just return that solution, right? If we are not happy with the pricing schemes, we make it finer, apply the same argument again, and come up with this up to 1 rupee solution. Okay? And that gives us an NV-free rent division scheme. All right? Pretty cool? Yes? All right. Okay. So we have solved one of the two problems. Okay. The second one, I'll try to just give you some hints as to how to solve cake cutting fairly. You should go back, try it on your own, and if you come up with a solution, you should write to me. Okay? So here are the hints. Suppose this is my cake. Okay, again, I draw cake in this very boring way. Cakes are much more exciting, but again, my drawing skills are limited. Okay? So let's say I come up with this division of the cake among 3 people. Okay, let's say I give this much to person 1, person 2, person 3. Okay? Just like in the rent division problem, we looked at the space of all pricing schemes. In the cake cutting problem, we look at the space of all divisions. Right? All possible ways to cut a cake among 3 people. Okay? We'll plot that space entirely, and that space can be captured also using a triangle. Right? So these extreme points are 1, 0, 0, 0, 0, 1, 0, 1, 0, meaning the entire cake goes to one person or the other, and in between you have all the fractional divisions. Yes? So this triangle here captures the space of all possible ways in which you make 2 cuts and give the cake to 3 different people. Okay? Right? So this particular cut here is like a point over here. Okay? And now we are going to do the same thing. We'll triangulate this. We'll come up with an ownership labeling. We'll ask everyone, if this is the cut, tell me which piece you prefer. Right? They'll point to their favorite piece. Again, apply Sperner. And again, that gives you an approximately NV-free division. Yes? So this is something that you should try on your own. Okay, I'm not doing it here. Go back, apply the same ideas from the rent problem to the cake problem and tell me what you find. Okay? Right? And again, you'll see a triangle of this form, and that gives you an NV-free division of the cake. Right? Okay. So I just want to conclude by telling you some other applications of Sperner's lemma. We have seen 2 applications, cake cutting and rent division. Let me give you just 2 more applications, because this is a very, very useful result. Right? It applies not just to cakes and rent, but to many, many other problems. One such problem is called the Monsky's theorem, which is the following. So here I've drawn 2 squares. Okay? The left square I've divided into 2 triangles of equal area. Okay? The right hand side square I've also divided into triangles of equal area. It's slightly harder to see, but this is 6 triangles of equal area that I divided the square into. Okay? Now Monsky's theorem says that if you're planning to divide a square into 3 triangles or 5 triangles or 7 triangles or any odd number of triangles of equal area, that is not going to be possible. Okay? So you can divide it into 2 triangles, 4, 6 and so on, but you can't into 3 or 5 or 7 or so on. It's a pretty cool fact, right? It's not obvious at all, and turns out you can prove this using Sperner's lemma. It's a fairly complicated proof. Maybe you'll see the ingredients of this proof in your advanced studies, not in school, but maybe in your higher education. But this is true. You can prove this using Sperner's lemma. Okay? Okay, here is another very cool consequence of Sperner's lemma. It's called the Brouwer's fixed point theorem. Okay, this was proposed by this mathematician called Brouwer. I have some complicated terms written here. Don't worry too much about it. Basically, the theorem says that if you have a function, everyone has studied functions? Yes, function f, right? So anytime you have a nice function, f, then there must exist a point x, which the function maps to itself. Okay, nice has a formal meaning in math. You'll see some of these terms again in your higher studies, so don't worry about it. But let me pictorially try to explain to you the consequence of this. Okay? So anyone recognizes this? What is this? Map of Delhi. That's where we are, right? Okay, so this is map of Delhi. Where is IIT? Somewhere here? South? Yes, near Saket and Hoskas? Yeah? Okay. Maybe many of you are coming from other parts, but right now we are here. Now imagine I take a map of Delhi, I put it on the floor, so it looks like this. This is slightly expanded, but imagine this, right? So I take the same map of Delhi, I put it on the floor. Then the theorem says that there exists a point on the land which is exactly on top of its location on the map. Right? There exists an x which is mapped to itself by this mapping function. Okay? That's a very cool consequence, right? There is at least one point on the map which the map gets right. Okay? That's pretty good. Okay? So you can prove that these points are called the fixed points, right? Because they are not altered by the function. They remain where they are. And this is an application of that. Okay? All right. Cool. So for example, this point here on the map is also on top of its actual geographical location. So that's pretty cool. Okay, so this is all I had to say. If you have any thoughts or comments, you can use this QR code to share, but otherwise I'm very happy to take questions. Thank you. Any questions?
सर हमने जो रेंटल
I'm sorry, I can't. Can we please let our friend
Hello?
ask a question?
सर
All right. Can I ask for a few minutes of silence, please? Let's do a quick round of questions.
सर सर हमने जो रेंटल हार्मोनी के अंदर स्पर्नर्स लेमा यूज किया था, हमने जो आउट ऑफ द बॉक्स हमने जो सोचा बड़ा ट्रायंगल बनाया था, व्हाई इट इज नेसेसरी कि हम 3 जो साइड है उसके सामने ही वर्टेक्स 3 रखें?
हाँ, because we wanted that none of the outer gray triangles end up being fully colored. If I don't do that, then I can't control that.
नहीं सर, हम 3 जहाँ पे हमने 3.3 वर्टेक्स को प्लेस किया था, वहाँ पे हम 0.1 भी तो वर्टेक्स प्लेस कर सकते हैं.
हाँ, we could have done that, but then we cannot guarantee that the fully labeled triangle would be inside. It can also be outside. Then it's not clear. So to guarantee that it's not outside, that's why we did it. We can talk more after. Yeah.
Okay, thank you, sir.
Yeah. So, so Shomik, should we take the questions in person or over here? Should we let people go and then do the questions individually? Okay. So let's do this. Anyone who has a question can stay back. I'll be around, and those who wish to leave may please do so. Okay. So I'll be around. Please come and talk to me. Right. Thank you.
Hello. Yeah. Okay, so let's thank Professor Vaish for a fascinating talk. Okay, so a big round of applause for Professor Vaish. Okay, so as a small token of appreciation for his talk. From the outreach committee of IIT Delhi. So, a little bit of memento for Professor Vaish.
Thank you so much.